Hi, in this tutorial we will go over linear filtering. We will base our study of this topic on the content from section 3.2 from the textbook, page 111. Um, we usually filter images as highlighted in this section in order to add soft blur, sharpen details, accentuate edges, and in most cases to remove noise. Let's go into the examples that are listed on figure 3.11, the examples from B to D, the figure A, the part A of 3.11 is going to be the original image, and then we're going to have examples of blur, how do we blur, sharpen, and accentuate. Okay, so these are the figures listed on figure 3.11. So A represents the original image, and then B is the blur image, C is the sharpener, and D is the one that presents the edges. So this is just an example of the results that we get when we apply the filters. We need to review an important operator that we will need for linear filtering that we're gonna call convolution. Let me see if we can go to the next page. So figure 3.10 has a very nice example about convolution. So to the left, where we have the f of x comma y, let's suppose that this is our image, and then here this is what we call the mask of the filter. So on the h of x comma y is what we call the mask of the filter, and what we do is that the mask of the mask of that filter, we place that on top of one of the given pixels. So let's say that the point 02 is the center of that mask, and we're gonna apply the convolution of the on pixel 96. So the idea is that somehow we're gonna use all the pixels that are around. So when you place this mask on top of that pixel, it's gonna cover all the pixels that are highlighted here in blue. So what we will do is somehow average the uh, elements, the all the intensity values that are around that pixel. But look at that, if you add all the numbers that are in this mask, it adds up to 1. So that's why we say it's kind of average, but we're average with some kind of a weight. So in this case, it says that the pixel on the center is more important than the neighbors, the contribution of the new value. So the pixel of the center is going to be 0.2, and then each one of the neighbors around the pixel is going to be 0.1. So how does the convolution works? Well, so when we're placing this on top of the pixels here, 0.2 goes on top of 96, and then the other 0.1s goes on top of 65, 98, 123. So the way that this works is we're gonna do 0.1 times 65 plus 0.1 times 98 plus 0.1 times 123 plus 0.1 times 65 plus 0.2 times 96 plus 0.1 times 115 plus 0.1 times 63 plus 0.1 times 91 plus 0.1 times 107, and the number that we should get there should be this 92 that is there. So we repeat that operation for every pixel on the image, and this will be the resulting image after we apply that operation. So this is an operation that we need to understand how do we do the convolution. So in the type of filters that we usually use, you see we adding, somehow we're taking into account all the neighbors of the pixels. So we could maybe have a filter in this case that, the mask has, that says that, let's suppose that only the pixel on the top of bottom, left, and right are important. Then my mask here in these corners will be 0, 0, 0. And if I consider all to be important, then I have 1, 2, 3, 4, 5 pixels. Then I can multiply each one for 1 over 5, and then that will be a possible filter. Let me give you other examples of filters that are in your textbook. So here are other examples of possible filters, and these are the masks that we call for those filters. Like for example here, this is a nice idea of a filter. Look, the center will be the pixel in which we're gonna make the convolution. So it says that this is, I mean, this intensity value is more important than the ones that are around that pixel. So look at that, this pixel that will be far away from there is going to be 1 over 256. Now you add all these numbers in the mask, it should give us 256. So divided by 256 should be equals to 1. The same here, if we add all these numbers, it should give us 16, and the same with this type of filter. Okay, so let's go back again to the figure on 3.10. Okay, one more time. So what is it that we want I mean, when we want to remove noise? So for example, in this area, so we're talking about this pixel, the 96. Then we say, well, maybe there is some noise, there is something that we want just to remove. Then what we're doing is we're looking into the neighbors. So we say, maybe, I mean, there was some type of distortion in the image, and it was, the noise is distributed, and then what we want to do is somehow average the pixels. So one idea will be like average all these 9 pixels and get the new value for this, but for that we're considering the neighbors. Now most people will say, well, the intensity value that is here is maybe not, I mean, kind of close to what it should be, so we should give a higher weight. So that's, for example, in this max the weight is 0.2 and the neighbors are contributing 0.1. So but we're recognizing, or giving usually we give a higher weight to the number that is there. Again, if I play with the numbers, let's say that, for example, here I say this is now 0.4, the weight for the pixel there, then I need to do some type of distribution here, or I can say maybe this is 0.4 and then this will be, so for example, the one in the center I say that is 0.4, and then I say that these are still 0.1, 0.1, and 0.1. You see these 5 pixels will give me 0.8. Then the corners I can do 0.05, 0.05, 0.05, 0.05. Why? So all these pixels add to 1. So it's kind of average with 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 some type of a weight.